All right, everybody. So good morning. Good morning. So we are going to be going over questions 51 to 59 for the August 2019 Regents. And so we're going to start with the first question. One of the things to definitely keep in mind is that when you're starting off with a question, you want to make sure that if they give you background information to know what questions that it pertains to. So it says, base their answers to question 51 to 53 on the passage below, the cross-section in your answer booklet, and on your knowledge of earth science. So 51 to 53 is going to be based on the passage, the answer booklet, and a knowledge of earth science. So the passage describes the discovery of ocean floor magnetism. The cross-section represents a pattern of normal and reverse polarity of the magnetic field preserved in the igneous bedrock of the oceanic crust. West of the mid-Atlantic ridge, the magnetic polarity pattern of the bedrock on the east side of the ridge has been left blank. All right. And so for question 51, you can do the reading. In question 51, it says, complete the diagram in your answer booklet by shading in the pattern of the normal polarity on the east side of the mid-Atlantic ridge center. Assume that the rate of plate movement are constant on both sides of the ridge center. Your answer must show the correct width and placement of each normal polarity section. All right, so when I take a look, all right, so when I take a look on the booklet, so basically we need to complete the pattern given right here. We need to complete the pattern given right here. So therefore, we need to fill in the magnetic polarity pattern. One thing that we know is that it follows the same pattern from the center going west is the same pattern from the center going east. So therefore, if 0 to 10 is shaded on the left, 0 to 10 has to be shaded on the right. If 10 to 15 is not shaded, 10 to 15 is not shaded. If 15 to 20 is shaded, then 15 to 20 on the right has to be shaded. If 20 to 30 is not shaded, then 20 to 30 on my right is not shaded. And if 30 to 40 is shaded, then therefore 30 to 40 will also be shaded as well. And so basically your diagram should look like as the answer key given right here. All right. Remember that it has to be symmetrical. Whatever's happening on the left, it from 0 has to be on the right. Are there any questions? Okay, let's move on to 52. So 52 states, identify the type of tectonic plate boundary at the mid-ocean ridges where these magnetic patterns were produced, okay? So we need to know the type. When you see the type of tectonic plate boundary, they're not looking for the actual name of a plate boundary. They're looking whether or not it's transformed, divergent, or convergent. One of these three, okay? So one of the landforms that's created from this type of plate boundary is mid-ocean ridges. So what page of the reference tables do I look that talks about plate boundaries? Page 5. So let's turn to page 5. And one of the things you notice is that every time that I see the word ridge, right, that represents a mid-ocean ridge, I see the same pattern over and over again. East Pacific Ridge, the plates are separating from each other. Southeast Indian Ridge, that's the mid-ocean ridge. The plates are separating from each other. Mid-Atlantic Ridge, the word ridge, the plates are separating from each other. What type of plate boundary is it where the arrows are separating from each other? And the correct answer is going to be divergent plate boundary. Every time we see a divergent plate boundary, we see a mid-ocean ridge. And so that's why the correct answer for 52 is going to be divergent. So you could have said the type, you could have said divergent, or you could have said divergent plate boundary for 52. Let's turn to 53. So 53 states, on your set of axes in your answer booklet, draw a line to represent the relationship between the distance from the mid-Atlantic ridge and the age of the ocean floor bedrock. Okay? So one of the things that we know in a mid-ocean ridge, new ocean floor or new crust is created at the very center of the mid-ocean ridge. So at this point right here is where we're getting new crust, right? Or you can say new ocean floor. All right, at the center. So therefore, that means that when you're further away from the center of the mid-Atlantic ridge, the bedrock is going to get older and older. The center of the ridge is the birthplace. I'll repeat again. The center of the ridge is the birthplace for new ocean floor. So I know, I'm just going to start on one side. I know that as I go further away from the center, it's going to get older on the east side. And the further I get from the center is going to get older from the west side. So if you have some sort of diagram that's V or U-shaped, right, getting further away from the ridge, and it should be the same heights and the same lengths, then your answer is going to be correct for number 53. Any questions? All right, let's take a look at number 54. Okay, so number 54 states, it says, base your answers to question 54 to 56. So whatever information is going to be given, make sure to highlight that we know that this diagram and the information below is going to help me for questions 54 through 56 only. Base your answers to question 54 through 56 on the photograph below and on your knowledge of earth science. The photograph is a rock sample composed of pebbles that have been cemented together. All right. Identify the name of this sedimentary rock. Well, what do we know about this sedimentary rock? We know that it's composed of pebbles that's been cemented together. Okay. And when I'm looking at the pebbles, they seem to be that they're definitely more rounded. Right? That's going to play a role when we identify what type of sedimentary rock is this. So what page of the reference tables do I look to find out the sedimentary, what sedimentary rock it is? Page 7. And so we know that it's not going to be chemically or organically formed because the only thing that this rock contains is pebbles. So it's clastic, and it only contains pebbles according to the reading. There are 2 rocks that contain pebbles. Sedimentary rock contain pebbles. Breccia and conglomerate. What's the difference between the 2? One is angular and one is rounded. When we look back on our problem, we see that the pebbles definitely look rounded. The pebbles definitely look more rounded than angular. So therefore, what that lets me know is that because I'm looking for rounded fragments, is going to be conglomerate. And so your correct answer for 54 is going to be conglomerate. Any questions? All right, let's take a look at question 55. So question 55 says, identify a total possible range of particle diameters in centimeters for a particle to be classified as a pebble. So we want to know the total possible range of particle diameters in centimeters for a particle to be classified as a pebble. There is one page on the reference tables that gives us the different range of particle sizes to be classified as a pebble. What page, everybody? Well, when you flip through, all right, I'm looking for keywords. I'm looking for particle size, particle size. And if you take a look, and I see it right here, page 6 of the reference tables, relationship of transported particle size to water velocity. So when I take a look, one thing I already noticed, they want to know the range for particle size to be classified as a pebble. So therefore, pebbles is in this range right here. So therefore, if I have a particle size that is 0.2 all the way to 6.4 centimeters, then that will be considered to be classified as a pebble. So therefore, on your answer sheet, your answer should be from 0.2 to 6.4 for your correct answer. Any questions? All right, let's take a look at number 56. So when we take a look at number 56, sorry about that, here we go. All right, so it says, describe the evidence from the photograph that supports the inference that the particles in this rock were most likely transported from running water. This is not a reference tables question. This is a knowledge of your earth science question. So we know that if particles are transported by running water, right, which is an agent of erosion, it's an agent of erosion, what are our rocks going to look like if it's transported by running water? So running water can be streams, and it could be rivers. So what do we know? How are my particles going to look? Is going to be definitely, what is the special characteristic about this rock that we notice, that we mentioned in 54? Is the fact that the pebbles are rounded. So because the fact that the pebbles are rounded, that lets me know that it was transported by running water. And your answers for the regions, these are the following answers that they would accept for 56. So you could have said any of the following. You could have said rounded pebbles, right? You see the keyword rounded pebbles. That's the best answer. Usually indicate transportation by running water. Sediments tumbling and bouncing in stream produces the round shapes. The particles are smooth and have round shapes. So the fact that you have to mention that the sediments and the rock has rounded particles, that will give you the correct answer. Let's take a look at number 57. Let's go. All right, 57. So once again, 57 and 59. And so it states, base their answers to question 57 through 59 on the diagram below and on your knowledge of earth science. The diagram represents a model of the disintegration of a sample of the radioisotope carbon-14, 14C. All right. And it says, so we know that carbon-14 is the black and the stable disintegrated product is the white. So 57, determine the number of carbon-14 atoms that would most likely remain at the end of the second half-life. So we know, if I count, let me see, how many carbon-14 atoms we have originally? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I started with 16. After one half-life, let's see how much is left, right? And remember, half-life describes that for a certain period of time, you're going to have half of your original sample. So after one half-life, how many carbon-14s do I have? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 after one half-life. What's the pattern? After one half-life passed by, half of it is remaining. So if we continue that pattern after your second half-life, right? If I have 8 left after my second half-life, how many would I then have? If the pattern is I'm losing half of it after every half-life. If I started with 16, it goes to 8. After my second half-life, I'm only going to have 4 left, right? And the rest would end up being the disintegrated product. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So once every half-life passes by, you lose half of your original isotope, and the rest gets converted to this stable disintegrated product. So the correct answer for number 57 is 4. We started with 16. After one half-life, we have 8 remaining. After another half-life, we end up with 4. Okay? Let's take a look at 58. Identify the stable disintegration product that is produced when carbon-14 decays. Now, carbon-14, where have I seen carbon-14 before? Where have I seen it? Where have I seen it? Let's take a look at our reference tables. All right, when I scroll through my reference tables, all right, radioactive decay data, and look what I see. I see carbon-14. And this tells me what happens when carbon-14 is disintegrated. What does it turn into? So 14C turns into 14N. So if you mentioned, and I'll put in the answer key, and this is for number 50, what number is this? 58. So here are, oh, sorry about that. Give me 1 second. Here we go. So you could have written any of these for the correct answer. If you said nitrogen 14, that would have been fine. If you said 14N, that would have been fine. If you wrote 14C arrow 14N, you would get credit for that as well too. All right. And then finally, let's take a look at 59. So we take a look at 59. So 59 says, identify the radioactive isotope that has a half-life that is approximately the same age as the estimated age of the Earth by using the radioactive decay data table in the Earth Science reference tables. So I need to know which radioisotope has a half-life that is approximately the same age as the estimated age of Earth. Where can I find the estimated age of the Earth first? I have to know where can I find that, all right? Lucky enough, it's not something that you have to memorize because it is on the reference tables. What page talks about geologic history, events of the Earth? There's only one page or 2 pages simultaneously, which is page 8 and page 9, all right? Now, when I'm looking at page 8, where do I see estimated time of origin of Earth in the solar system? If you look on page 8, it says it right here. And so the answer number that I got is 4,600. But we have to remember, 4,600 what, right? What is this number? Is it years? Well, let's see, 4,600. And it's million years ago. So that means that I need to find a radioactive isotope that has 4,600 million years. And when I write it out, 4,600 million years is the same as 4,600,000,000. All right. So I need to find an isotope that has 4.6 billion years. Which isotope is close to that? All right. And so the isotope that they give me here, all right, let's take a look. The isotope that they give me here, I see 1, 2, 3, 4. So let's see if I write out the number, okay? So when I write out the number, 5.7 times 10 to the 3 is 5,700 years. 1.3 times 10 to the 9 gives me 1.3, right? If you do this on a calculator, 1.3, you end up getting 1,300,000,000. 4.5 times 10 to the 9, 4.5. You move it to the right 9 decimal places. 1, 2, 3, 4, 5, 6, 7, 8, 9. You fill the spaces with zeros. And so when I write my new answer, you end up getting 4,500,000,000. And then rubidium, 4.9 times 10 to the 10, gives me 49 billion. So which one is closest to 4.6 billion as we solved? The 4.5 billion right here. That's the closest to it. And which one was that? Uranium-238. And so that is your answer. Uranium-238. If you have any questions, let me know. Stay tuned for the rest of the videos that will be uploaded next.